seen what the tangent space to a hypersurface is. Now we are going to generalize the same notion to an arbitrary manifold. As I had remarked when we solved, or rather proved, that the tangent space to a hypersurface actually coincides with our intuitive visualization of such a tangent space, I had remarked that time that please understand this lemma carefully. It will be very useful in the study of manifolds. Well, the time has come where that understanding is going to be called. The three definitions of manifolds will give rise to three ways of thinking about the tangent space. We will define three vector spaces using the three definitions, and it will turn out that all three vector spaces are exactly the same and they confirm to our intuitive idea of what the tangent space should look like. So let's state the three definitions of the tangent space. Definition: let M subset of Rn be a d-dimensional CK manifold. We define for A in M the tangent space TAM to be number one, when we view the function the manifold as locally the graph of a CK smooth function, then we define it to be just the image of DFB where f of b is equal to A and M is the graph of f near A. Okay, and of course f is a CK smooth function. So I'm more or less borrowing the notation from the definition of a manifold. The first definition was that it's locally the graph. So if it's locally the graph, just look at the image of the linear map DFB. Note that map we already know is going to be of rank D. So the image of DFB will be a d-dimensional vector space. The second definition is when we considered the manifold as locally the level set of a CK smooth function. And I'm just going to not bore you with notation once again. I'm just going to say the kernel of DGA. And to understand what this G is, please refer back to the definition of the manifold. I'm just borrowing the notation from the definition of the manifold. Okay. And third is when it was locally parametrized near A, and there it's just the image of dH of B where h of B is equal to A. Okay. So these three are the three ways of representing the tangent space. Now again, the third definition will give rise to a d-dimensional vector space simply because dH is also of rank D, and the kernel of DGA, that's also going to give you a d-dimensional d-dimensional vector space simply because DG was rank n minus D. The rank nullity theorem will tell you that the kernel will have to be of dimension D. So thankfully at least all these three definitions will give rise to spaces that are at least same dimension. Now we are going to show that not only are the spaces the same dimension, they are exactly the same. Not only that, notice that there is a choice involved. Okay, now there is no such result that says that near A the manifold is the level set of a unique function. I could have chosen some other function G for which the manifold locally near A, it's the level set of that function also. That's possible, and similarly you can have many parameterizations of a manifold. So it's not even clear that when you make a different choice of these spaces, of these functions, you get the same spaces. That's not clear either. So to make sure that this definition is well defined, I have to show two things. For a given choice of f, g and h, they all should coincide, and if you change also, you should still get the same space. Okay, now I'm going to leave it to you to think about why it suffices to show that let me just write that down. It suffices to show that the second and third space coincide. Third spaces coincide. If I show that all of this is taken care of and everything else is automatic is my claim, this is something that you should ponder about why this is true. I'm just going to show that the second space and the third space coincide and everything is taken care of. Okay, now observe, to show that the second and third space coincide, observe that GOH is a map from U. Again, I'm borrowing the notation from the definition of a manifold. GOH is a map from U to Rn minus D, that is precisely the zero map. It is precisely the zero map. So there is no need to say this. Okay, observe that G circle H from U to Rn minus D is the zero map. Why is it the zero map? Well, simply because H maps on to a piece of a manifold and G takes that piece to 0. Okay, so what I'm assuming, I'm technically assuming that H of U is contained in the domain of G, which I can do by continuity of H and just shrinking U if necessary. I can assume that H of U is fully contained in the domain of G. Okay, now what does the chain rule say? It says that DGA DHB is the zero map, is the zero transformation, the zero linear transformation. Well, that just means that image of DHB is contained in the kernel of DGA. It's precisely under this scenario will it happen that DHA composed or multiplied by whatever, let's put a circle to make sure there's no ambiguity. DGA composed with DHB is identically the zero transformation. That will happen precisely when image of DHB is contained in kernel of DGA. But both are d-dimensional, as I remarked at the beginning of this proof. Both are d-dimensional and therefore must coincide. And therefore must coincide. So this takes care of the proof. I still leave it to you to ponder about why everything else is automatic. Okay, so now let's move on and ponder about what is it that we have done. We first studied differentiable maps from open sets in Rn to Rm, and we saw that these are supposed to be, the derivative maps are supposed to be the best linear approximation of such a differentiable map. Now we have approximated the manifold locally by the tangent space. Just like a manifold, just like a map is approximated by the derivative which is linear, the manifold, which is in general a curved object, is approximated by this linear subspace which is the tangent space at this point. So it's natural to wonder that if you have a differentiable map from a manifold, is it automatically true that that differentiable map is going to give rise to a derivative that approximates this map, but approximates it where? Approximates it on the tangent space. So we have derivative is linear approximation of map of a differentiable map. We have tangent space. Tangent space is linear approximation linear approximation of a manifold. Can we combine these two and start with a differentiable map on a manifold? Differentiable map on manifold and approximate by a derivative map on the tangent space, So I'm just combining both. Is it possible to do this? Well, yes, we can do this. So that's the next definition. Let M subset of Rn be a C1 manifold, and let F from M to Rm be a map. Okay, we say F is differentiable at a point A in M if for some parametrization H from U to M, so some local parametrization near A, we have F circle H is differentiable at the point H inverse A. Okay, so essentially the picture is as follows. You have a curved manifold and you have an open set that parameterizes a piece of this curved manifold. You have a map from F to some other Euclidean space. Okay, so I'm just let me draw it properly. To another Euclidean space, I have this map F. To say that F is differentiable at A, you just sort of pass to an open set in Rd via this map H and check differentiability at this point, which maps to A. Okay, so this is perfectly a natural definition. The manifold is parameterized by a C1 smooth function, pass to a Euclidean space, open set in Euclidean space via this C1 smooth function and define differentiability there. Okay, so this tells you when a function is differentiable, but this doesn't tell you what the derivative map is. That is the next part of this definition. If F from M to Rm is differentiable, then for a point A in M, we define DFA from TAM to RM as follows. If V is an element in the tangent space and W is a vector in Rd such that dH of B at W is equal to V. So I'm assuming H of B is the point, B is the point that maps onto A under the parametrization. So if you consider the parametrization and you know that the tangent space is the image of dH at B, so given a vector V in the tangent space, you can find a vector W in Rd such that DHB V equal to W, DHB W equal to V. So you make these choices, then DFAV is defined to be D F circle H at B of W. Okay, so this will be an element of Rm. Okay, so this is the definition of the derivative map. Again, the basic idea is you just pass on. So this vector v is sort of, let's draw an inaccurate picture. So let's say this vector v is like this. Well, you just look at that vector w that maps onto this by dh of b, dhb, and then see where this vector w goes under the composition f circle h. Take the derivative map and see where it goes. That's the image. So again, there are some issues of well-definedness under this definition. There is no unique parameterization. There could be dozens. It's not clear that this map that we have defined DFA is not clear that it is linear as well. So we have a proposition that clarifies all of this in a neat way. Proposition with the notation as the previous definition. Notation as the previous definition. Okay, let h1 from, let's say, u1 to m be another local parameterization for m near a. Then we have three facts. Number one, f circle h1 is differentiable at h1 inverse of a. So in the definition of differentiability, all it says is, therefore some local parameterization this happens, that f circle h is differentiable at h inverse a. It's not clear that if I had chosen a different parameterization, f circle h1 at h1 inverse b, h1 inverse a, it's not clear that it's going to be differentiable. That needs to be asserted. So this definition is sort of independent of parameterization. So we want that. We want the definition of differentiability to depend only on the manifold and not a particular choice of parameterization. And in fact, our definition does indeed is indeed independent of the parameterization. The same, if it's differentiable under one parameterization, it's differentiable under any. Second point, the derivative map DFA is well defined. That means if you had chosen a different parameterization, you won't end up with a different derivative map. And finally, the derivative map is linear. The derivative map is linear. Okay, so the proof involves one idea which requires you to now go back and watch the video about the definition of a manifold. Okay, so let's prove all of this. I will mention what is it that you must check from the definition of a manifold video. Please go check that or check the lecture notes for this. I have made a remark about this. Let h from u to m be the parameterization near a such that h of 0 is equal to a and f circle h is differentiable at 0. Okay, now if you look through the definition of a manifold, the proof that all three definitions in fact give rise to the same, I mean each definition is equivalent to the other. At one stage we go from a parameterization to a local level set, and the way we did that was we considered this map h, which is supposed to be a parameterization from Rd to Rn, and we tagged on some extra variables to make it a map from Rn to Rn, and argued that that map is going to be, the derivative is going to be invertible, and you applied the inverse function theorem to get an inverse. Okay, So using that inverse, you can actually say something about this parametrization. What is it that we can say? Well, from the proof of 3 implies 2 in the definition of a manifold, we can assume that we can find a C1 smooth map, which we call H inverse for simplicity. You will understand why I am using this notation H inverse, okay, such that H inverse is from W to RD and H inverse restricted to M intersection W is the inverse of H. Okay, so again let's draw a bad picture to have good understanding. We have a manifold, we have an open set, and we have this H that parameterizes this. We know that H inverse is a continuous thing, and this is supposed to be M intersect W. W is an open set which is larger, it's in Rn. Okay, so what this says is you can find a map H inverse which is defined on this W, which is a C1 smooth map, okay, and H1 inverse maps W to RD, and when you restrict H1 inverse to M intersection W, it's not H1 inverse, H inverse, when you restrict H inverse to M intersection W, it is indeed the inverse of H. Okay, so what this achieves for us is H inverse was a priori just a map defined on a piece of a manifold. We can't really talk about smoothness of a map that is not defined on an open set. This extension allows us to talk about smoothness of H inverse. The fact that you can extend H inverse, which is just defined on a small piece of the manifold, to an open set in Rn allows us to talk about the differentiability of the inverse map. Okay, so please check the proof of the fact that 3 implies 2 in the definition of a manifold to understand why this is true. Okay, now to achieve this, actually I must to achieve this we may have to shrink U. Okay, that's because we have to apply the inverse function theorem and all that, and inverse function theorem is a local result, so you might not be able to get the map H, that is we had first of all made this map H into a map defined on Rn, and then inverse function theorem will give you a small neighborhood. It's not clear how big that neighborhood is. Okay, so you may have to shrink U. Also look through the remark in the notes following the 3 definitions of manifold. I have talked about this at some detail. Okay, anyway, this is not so difficult. It will be a good exercise for you to work this out, why this is true. Okay, we can also assume that H inverse of W is contained in U. Just shrink W if this doesn't happen. H inverse is anyway continuous, so you can do this. Okay, now let B be in U1 such that H1 of B1 is also A. Remember, H1 was another parameterization, and it will be defined in a different open set U1 that might not even contain 0, but there will be a point that maps onto A. That point we are calling it B1. Okay, now let B be a small ball around B such that this H1 of B also maps to this W. Okay, this W neighborhood comes from the definition of the manifold with respect to this parameterization H. Okay, again look through the notation in the definition of a manifold to understand what this W is. There will be a W corresponding to H1 also, but that could be very different. But again, by continuity, I can just find a ball such that H1B is contained in W. Okay, now here the next equation is the crux of the proof. Then F composed with H1 restricted to B is nothing but F circle H circle H inverse circle H 1 restricted to B. Okay, so the composition of F and H1 restricted to B is nothing but composing F and H, then composing that with H inverse composed with H1. Essentially these two just cancel off. Okay, this is completely elementary, just H and H inverse just cancel off. So you get F composed with H1 restricted to B is nothing but F composed with H composed with H inverse composed with H1 restricted to B. Okay, now observe that the way we have set up things, H inverse composed with H1 restricted to B of B is nothing but 0. Why is that the case? Because H1 takes B to A and H inverse will take A back onto 0. Okay, so this will show that H inverse composed with H1 restricted to B of B is nothing but 0. Okay, and this composition is smooth. Composition is C1 smooth. Why? Because this map is C1 smooth at the point 0, and this not sorry about that, this composition is not C1 smooth, this composition is differentiable at B. Why is it differentiable at B? Because this is differentiable at 0 by hypothesis, and this is certainly going to be differentiable at all points because both maps are actually C1 smooth. So what this shows is that F composed with H1 restricted to B is differentiable at B. Now differentiability is a local property, and therefore you can conclude that F composed with H1 is differentiable at 0. Excellent. So the definition of differentiability does not depend on the choice of parameterization. Now on to the second part. The second part asserts that the definition of the tangent space, the tangent map, the derivative map from the tangent space is well defined. Okay, so let V be in the tangent space and let W comma W1 in RD be such that DH of 0 of W is V and DH1 of B of W1 is V. Okay, now the goal is to show that DF circle H at the point 0 of W is equal to DF circle H1 at the point B of W1, so that both images are the same, therefore both derivative maps defined using the parameterization H and the derivative map defined using the parameterization H1 are both the same. Okay, now what we are going to do is we are going to pull the same trick. DF composed with H1 of B of W1 is just DF circle H, F composed with H at 0, then D H inverse composed with H1 restricted to B at the point B of W1. This just comes immediately from the first part, and this is nothing but D of F composed with H at 0, then D H inverse at the point A of DH1 at the point B of W, which is just V. Okay, so the final composition, I am applying the chain rule and writing DH inverse at the point A, then DH1 of at the point B of W1, but DH1 of at the point B of W1 is just V. Okay, now this is nothing but D F circle H at the point 0 of W, and I want you to check why this is true. That D F circle H at 0 of W is equal to this expression here. Okay, so one part, the assumption that I'm making is D H inverse A, DH inverse 0, DH inverse A of V is W. This is what you have to justify. Okay, so this concludes the proof of well-definedness of the map DFA. Finally, we have to show the linearity. For linearity, if V1, V2 are in the tangent space at M, then there exists W1, W2 in RD such that DH of 0 of WI is VI. Okay, then DF at the point A of CV1 plus V2 is nothing but DF circle H at 0 of CW1 plus W2, because under the map DH0 CW1 plus W2 will get mapped onto CV1 plus V2, and this is nothing but CDF composed with H0 of W1 plus DF circle H composed with 0 of W2, and this proves the claim. Linearity follows. Okay, so this shows that the derivative map is not only well defined, it's also linear. So this concludes this video on tangent spaces. Please do check out the exercises where we relate this tangent spaces to curves which are natural, and that will also strengthen your intuition as to why this is the correct definition of the tangent space. Whenever you're dealing with abstract stuff, you have to understand that the abstraction coincides with our intuition, and these exercises will do that for you. This is a course on real analysis, and you have just watched the video on the tangent space to a manifold.